my name is Mariano Zeron, and in this video I'm going to show you how to carry out operations between MoCaX objects. In particular, given two MoCaX objects, I'll show you that we can add them together to obtain a third MoCaX object, and if you've got a MoCaX object and a constant, you can multiply them to get a second MoCaX object. So I've prepared this example for you where I have two functions, f1 and f2, which are the sine and the cosine function. And I quickly added them up and defined this function called sum function, which is just the addition of f1 and f2. So what I want to show you is that you can do the following thing. I'm going to build a MoCaX object for f1 over here. So I built it and printed it out so that you see it down here. Equally, I can build a MoCaX object for the second function. Now, instead of building a MoCaX object for the sum of f1 and f2, what I'm going to do is just add the MoCaX objects. And the way that you do it is by using the addition operation, which we've overloaded to give you a third MoCaX object, which is the addition of MoCaX object 1 and MoCaX object 2. And then what we do down here is we want to compare the accuracy, or we want to see what the accuracy is of MoCaX object 3 with respect to some function, which is the sum of f1 and f2. So MoCaX 3 is not an object that was built by asking some function to return values. It was obtained only from MoCaX object 1 and MoCaX object 2. So let's see what happens when we evaluate it. And then when we plot the values returned by the third object and the sum function. And we see that they're pretty much the same. And the error on the right-hand side is really good, 10 to the minus 6, roughly. So this is addition. Multiplication by a constant would be very similar. So you can just take you literally do a times MoCaX object, let's say 1, and that should return another MoCaX object, which is just the scaling of MoCaX object 1. So this example is pretty straightforward. You may even think, why do we even bother adding MoCaX objects, even though the addition is super quick because it just amounts to adding coefficients? Why do we bother adding the object if we can just build the object from the sum function? So there are certain kind of situations that you will encounter, like for example, let's say that you've got a netting set that consists of a single trade type, like a swap. But the collection of swaps vary in terms of notional, in terms of maturity, moneyness, and so on. But they rely on the same underlying risk factor. So you can definitely add the pricing function of each of those trades and obtain a pricing function that represents the whole netting set. And you could decide to build a MoCaX object for that final pricing function and use it. That's perfectly fine. Or it may be more convenient, depending on your situation, to build a MoCaX object per trade. But then at the end, you don't need to construct a MoCaX object for the whole netting set. You can just add each individual MoCaX object, which is really quick, and you obtain a final MoCaX object which represents the whole netting set. Now the advantage is if you're running a risk calculation, you will need to call, in principle, if you didn't have a MoCaX object for the whole netting set, you would need to evaluate each MoCaX object throughout all the nodes of the simulation. And even though each MoCaX object is evaluated very, very quickly, you don't want to be evaluating thousands of them. So you compress them into a single one using the addition operator, and then evaluate that single MoCaX object, which will save quite a bit of time. So that's one thing that you could use the addition for. But also, now that you've got a MoCaX object per trade and the MoCaX object for the whole netting set, you can engage in exercises like the following. Let's say that you're interested in optimizing some metric of your portfolio, some XVA metric, for example, of your netting set. So what you can do is, first of all, calculate that metric for the whole netting set that you can do using the MoCaX object for the whole netting set. But then if you've got possible incoming trades, you can build the MoCaX object for a possible incoming trade, add it to the MoCaX object of the netting set, and run again your calculation. That is going to be really quick, so you'll get the new metric and see whether or not it's convenient to add that extra trade. If it is not convenient, go to the next trade. And you can carry out this exercise covering a wide range of trades in a very short period of time, which will allow you to optimize your portfolio in ways that probably you wouldn't be able to do before. In the same way, if you want to get rid of a trade you think may be better for your netting set, one of the things that you can do is, given that you've got a MoCaX object for the whole netting set and a MoCaX object for each individual trade, you can simply subtract one from the other and run again the calculation to see what your new metric would be without that trade. And you can engage in all sorts of exercises like this. So the addition has its use in day-to-day practice. But also the multiplication by coefficients can be quite useful, because it allows you, for example, given a MoCaX object that represents a particular trade, say a Bermudan swaption, that was built for a particular kind of notional, if you want a different trade, or a trade which is identical with the exception of the notional, what you can do is multiply that MoCaX object by the corresponding coefficient to adjust for the notional, and in no time you'll have a new MoCaX object that replicates the new trade, instead of having to build a new MoCaX object from scratch for the new trade. And this can be quite convenient in settings where perhaps you always know what the standard trades for the day may be. Because once you've built a MoCaX object for each one of them, then you can just scale them according to the notional that may change, and you've got your new object without any effort whatsoever. So it's as simple as that to carry out operations for MoCaX objects, and it has its uses as I've illustrated. Thank you very much. See you in another video.